Assalamualaikum everyone. Welcome to Fundamentals of Programming course. In today's session, we plan on discussing about pointers. But before diving deep into the understanding of pointers, one important concept needs understanding, and that is of RAM, random access memory. We know that the variables that are used in our programs are stored in RAM. Let's understand the basic architecture of RAM, how the RAM is actually built at the back end. So RAM, we can suppose that we have a 4 GB RAM, and here the assumption is that the width of our RAM is 1 byte. It can be 2 bytes, 4 bytes, but for the ease of understanding, the width of this RAM that we are discussing here is kept to 1 byte. And we assume that we have a 4 GB RAM. What does it mean to have a 4 GB RAM technically? 4 GB basically means 4 gigabytes, and giga is basically equals to 10 raised to the power 9. And 10 raised to the power 9 means that we have basically 9 zeros after the 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. So when we convert it into the number systems for our better understanding, we observe a phenomena. We see that this number that we have becomes roughly equal to, actually 4 GB is not exactly equal to this, it is exactly equal to this number. However, for the ease of understanding, we have developed the rough estimate that basically says that this number, if we talk about in Pakistani number system, becomes equal to unit 10, 100, 1000, 10,000, lakh, 10 lakh, crore, 10 crore, Arab, 4 Arab bytes. So 4 GB in this number system becomes equal to 4 Arab bytes. So if the RAM is built considering that the width of the RAM is 1 byte, we will need to place 4 Arab bytes on top of each other in order to build a 4 GB RAM. Similarly, if we see it in English system, it becomes unit 10, 100, 1000, 10,000, 100,000, million, 10 million, 100 million, and billion. 4 billion bytes will need to be placed on top of each other in order to make a 4 GB RAM if the width of the RAM is 1 byte. So that is what it means to have a 4 GB RAM at our disposal. If the width of RAM is considered to be 1 bytes, we are either placing 4 Arab bytes on top of each other or 4 billion bytes on top of each other. So that is the basic architecture of RAM. Now every single byte of the RAM needs to be accessed, and it needs to be accessed distinctively. So in address in decimal, if we talk about the addresses in decimal, just like the houses have addresses, house number 0, maybe house number 0 is not there, house number 1, house number 2, house number 3, up to so on, house number, whatever the sector holds the number of houses. Similarly, we have the addresses of RAMs. For example, the first byte is addressed by the address 0, the second is addressed by the address 1 if we are talking about the addresses in decimal. The third byte is addressed by 0, 2, then 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, up to so on and so forth. It will go up to the counting of 4 giga. 4 giga addresses. So if we are talking about in decimal. In decimal number system, what we have is that we have the digits from 0 to 9. When we reach the 11th byte, we cannot distinctively identify the 11th byte with a single decimal digit, because a single decimal digit has just 10 possibilities: 0, 1, 2, 3, 4, up to so on 9. A single decimal digit has only 9 possibilities, and if we only 10 possibilities, and if we have to access the 11th byte, we need to introduce a second hexadecimal digit. That is basically 10, then 11, 12, 13. And similarly, when we are going to access the 101st byte of the RAM, we will need to address that byte distinctively with the help of third decimal digit if the addresses are in decimal. However, actually the addresses are not in decimal, and we will see a reason for that. Similarly, if we go on downwards in the RAM, if we have to access the 1001 first byte, it basically needs addition of another decimal digit. We need to add decimal digits as our RAM is growing. If our RAM was only 10 bytes long and our addresses were in decimal, one of the one decimal digit would have been enough. One decimal digit would have been enough in order to access those 10 bytes. Similarly, if we had 100 bytes, two decimal digits would have been enough to access that particular RAM's every single byte distinctively. And if we have a 1000 byte RAM and our addresses were in decimal, our three decimal digits would have been enough to access each single byte separately. However, as we go on, we need to add our decimal digits. However, if our addresses were in hexadecimal and hexadecimal addresses are represented with a 0x before the address number. Here the address number was not written along with the symbol 0x because these addresses were in simple decimal, and when we are normally writing the counting as we are writing here, we do not need anything to specify that it is in base 10. However, when we are writing them in hexadecimal, we have to write 0x with the addresses so as to indicate that these addresses are in hexadecimal numbers, not decimal numbers. Because if we do not write 0x, there will be a confusion if this 10 arrives and this 10 arrives. They are two totally different things in two different number systems. So that is why we need to write a 0x along with that so as to indicate that it is a hexadecimal 10 which equates to 16, not the 10. And this is a 10 which basically equates to 10. This is 10 in hexadecimal that equates to 16 in decimal basically. So this identification of 0x along with these things is very important when we are writing our addresses in hexadecimal numbers. Now when we have to access in hexadecimal number systems, we have 16 different. Hex is basically stands for 16. In hexadecimal basically stands for 16. Hex, sorry, does not stand for 16. Hexadecimal stands for 16. In hexadecimal number system, we have 16 different possibilities. Just like in decimal number system, we had 10 possibilities from 0 to 9. Here we have 16 different possibilities from 0 to F. From 0 to F, and they go from 0 to 9 first, and after 9 it is A, B, C, D, E and F. A, B, C, D, E and F. So 10 are these, 11, 12, 13, 14, 15, 16. So these are the possible hexadecimal digit numbers that can be written with a single hexadecimal digit. For example, when we were talking about decimal numbers, we could only write 10 different numbers from 0 to 9 if we had only one decimal digit at our disposal. Similarly, when we have one hexadecimal digit at our disposal, one hexadecimal, and this was one decimal, we can write 16 different things here: 0, 1, 2, 3 up to 9, and then A, B, C, D, E and F. So this extends our range of accessibility with a single number, a single hexadecimal digit. Just like here, if we wanted to access 16 bytes, we needed to have two decimal digits in order to distinctively identify every single byte. However, when we are talking about hexadecimal and we have a RAM of 16 bytes, suppose, we do not need to use a second hexadecimal digits because the number of possibilities for a single hexadecimal digit are larger than the number of possibilities for a single decimal digit. Similarly, when we move down the RAM, we see that here when we had reached 100 bytes, we needed to add another decimal digit. That is basically the third decimal digit in order to access that byte separately. However, since our possibilities in hexadecimal number systems are larger than that of the possibilities in decimal number system, so we need to add the third byte at 256th byte. We need to add third hexadecimal digit at the 256th byte, not the 101st byte. So that is another difference, that we need to add another hexadecimal digit to our hexadecimal addresses at the 257th byte. However, here we needed to add the third decimal digit to our decimal addresses after just 100 bytes. And similarly, when we go down, here we needed to add another decimal digit after 1000 bytes. Similarly, if our addresses were in decimal. Similarly, here we need to add our byte after 4096 bytes. We need to add another hexadecimal digit after 4096 bytes. So as we move down the RAM and our RAM size gets larger and larger, we see that this difference also gets larger and larger. Here we needed to add the third hexadecimal digit at the 256th byte if our addresses were in hexadecimal. However, here we only needed to add the third decimal digit after 99, and here we need to add another decimal digit after 999 when we are dealing with addresses in decimal. However, here we need to add the fourth hexadecimal digit at the 4096th byte, after 4096th byte. So that is one of the reasons that we express our addresses in hexadecimal number system and not the decimal system. Another important thing that we do, that why we do this thing, is because every single hexadecimal digit can basically be represented as 4 bits. From 0 up to F, 0 to 9, A, B, C, D, E, F. Every single hexadecimal digit can be represented as 4 bits directly. However, these decimal digits cannot be represented directly. Just like this 13 cannot be represented as the 4 bits 3 and a 4 bit 1. No, this is wrong. However, the 13 that will come here in hexadecimal, that can distinctively be written in terms of 4 bits, every hexadecimal digit. This can be represented as 0001 and 3 can be represented as 0011. So every hexadecimal digit can be represented at the back end in terms of 4 bits. So that is another reason why we express our addresses in hexadecimal number system. So and if we have addresses in hexadecimal number system, it means that we have to access a 4 GB RAM. 4 GB, if we had, let's make a certain assumption here. If our RAM was just 2 bytes long, it would need just a single bit to access every single byte distinctively. A 0 to access this byte and a 1 to access this byte. Similarly, if our RAM was 4 bytes long, we needed 2 bits to access every single byte separately. 00 can access this particular byte, 01 can access this particular byte, 10 can access this particular byte, and 11 can access this particular byte. We can no longer, if our RAM is extended to 4 bytes, we can no longer access every single byte separately with a single bit. This will not be happening. We need to add another bit. Similarly, whenever RAM gets to 8 bytes, basically 1, 2, 3, 4, 5, 6, 7, 8 bytes, we can no longer access it through every single byte distinctively with a single bit or 2 bits. We need to access every single byte with 3 bits. So as you see that here the number of bits was 1. So 2 की power 2 raised to the power 1 is basically 2. So 1 bit can access 2 bytes of RAM distinctively. Similarly, here we had 2 bits. It means that 2 bits can access 4 bytes of RAM distinctively. Similarly, here our addresses needed to be of 3 bits, and it means that the 3 bits can access 8 bytes of RAM distinctively. And if we move up and we want to access, our RAM is not 2 bytes long, not 4 bytes long, not 8 bytes long, it is 4 gigabytes long. And if we see what corresponds to 2 raised to the power 3 to access the 4 GB RAM, so it comes out to be 32. If we raise this number, for example, 1 bit can access 2 bytes of RAM distinctively, 2 bits can access 4 bytes of RAM, 3 bytes, 8, 4 bytes, basically 4 bits, sorry, 4 bits can basically access 16 bytes of RAM, 5 bits can access 32 bytes of RAM, 6 bits can access 64 bytes of RAM, and if we move on like this in 2 raised to the powers and we get to 2 raised to the power 32, it becomes equal to this number, and it means that with 32 bits we can access 4 GB RAM every single byte distinctively. And what does 32 bits means? 32 bits basically means 8 hexadecimal digits, because one hexadecimal is 4 bits, or 4 bits is 1 hexadecimal, so 32 bits is basically 8 hexadecimal digits. So that is basically the concept of RAM. Now let's look at a little example here. Now let us look at a little example here. This RAM is basically our variables are stored in the RAM by the operating system, whether it is Windows, iOS, MacBook, or Android. This basically operating system makes a decision about which RAM is free, and it stores the variable there. So if the RAM is free in the starting, it will locate the variables when they will be defined in your program there. If the RAM is free at the end, it will place there. That is basically the duty of the operating system. So here we have defined 3 different variables, VR1, VR2, VR3. We say that these things are basically already filled up with some other programs data. So this RAM is the first thing that we have free at our disposal. So what operating system will do is that it will basically store this variable 1, 2, 3, 4. It will store this variable here. So VR1, we know that when we have a variable, it is like a box in the memory, and it has certain name, it has a certain value. So it will basically be placed at this address. Now if we have another variable after that, the data type of this variable was integer, so that is why it took 4 bytes, 1, 2, 3 and 4. Now we have another integer variable named VR2. It will be stored here, 1, 2, 3, 4. It will be stored here at this particular address. It is also of type int, so it will also take 1, 2, 3, 4 bytes. We have another variable, and it will be stored 1, 2, 3, 4. It will be stored here, 1, 2, 3 and 4. It will be stored here. So this is basically the box of VR1, this is basically the box of VR2, and this is basically the box of VAR3. They are stored here. When we want to access these addresses, we know that these addresses will be basically in 8 hexadecimal digits, and they will be represented, they can be accessed when we put the ampersand sign before the variable name. For example, we write ampersand VR1 and VR1, so it basically gives this particular address. 3, 4, 5, 6, 7 and 8 will be 6. Assuming that the RAM was free here, it is basically 0, 0, 0, 0, 0, 0, 0 and 6. 7 zeros and 6. We know that it will be 8 hexadecimal digit long address because our RAM is 4 GB long, assuming our RAM is 4 GB long. Similarly, the address of second variable can be accessed by writing the ampersand sign along with that variable name. So that variable is basically stored here. So what address will be displayed on the screen? 00000000A. So this will basically be the second address. It is in hexadecimal, we know by 0x, and it is 8 hexadecimal digits long. Now you can see that in between 6 and A there is a difference of 4 bytes, and that indicates that first variable that was stored at this address was of type integer, because integers take 4 bytes. Similarly, if it was short int, it would have taken 2 bytes, and here the address would have been 8. Similarly, the third variable is stored here. So its address will basically be 0000000 and E. A, B, C, D are basically 4 bytes that are covered by this variable V2, VR2, and if it were of some other data type, it would have occupied in the bytes accordingly. Similarly, the third address has a difference between A and E, and that difference between A and E is also of 4 bytes. So that is how variables are stored in the memory. This is our first variable here, this is our second variable here, and this is our third variable here that is stored in the memory. So that is basically the concept of random access memory that needed understanding before starting the concept of pointers. Now when we have understood the concept of RAM, we now start to understand the concept of pointer definition. Pointers are basically the variables that hold the addresses of some other variables. Normally when we are using variables, they are used for holding some values. However, the pointer variables are used for holding certain addresses that are basically of some other variables, and there is a slight difference in their definition as well. When we are defining basically simple variable, what we write is that we write the data type and we write the variable name, and if we are initializing that as well, the simple variables are basically initialized by some values, so we write the third thing, that is a value. Now we know that the pointers are special kind of variables that hold addresses of other variables. So when we are defining a pointer variable, we need to put an asterisk before that. We can put the asterisk along with the data type name as well, and with the name of the pointer variable as well. Both are the fine. So we need to put an asterisk to indicate that the variable we are now defining is a pointer variable and not a simple variable. Simple variables, just like simple variables used to hold values, pointer variables hold addresses of certain other variables. So I have named the variable here for better understanding, and pointer variable here for better understanding. So here we have a variable. When we write this line of code, we have a variable that name is also variable here. It has a certain value 5, and it has an address. We know that in RAM it is stored at a certain address. For example, the first 4 bytes were filled with the data of some other program. So when we run our program, it will be allocated this space, this particular 4 bytes. 4 bytes because this is of type int. If it was of short int, so it would have been allocated 2 bytes. So this is the address at which this variable is located. This is the address, basically this one, 1, 2, 3, 4 bytes. So this is the address at which variable is located. Now a variable holds value, and the pointer variable holds the address of some other variable. This was basically the address of this variable, this was name of this variable, this was value of this variable, this was address of this variable, and pointer variable hold the address of some other variable. So when we define the pointer with star asterisk pointer variable, the pointer variable was defined, and now compiler knows it is not a simple variable, it is a pointer variable, and it will hold addresses of some other variable. So it basically holds the address of basically another variable named variable here. So that is what that is how pointers are defined and initialized. Now this particular statement here means that pointer variable is a pointer to integer, It means that where this pointer variable is pointing to the address of the variable, that variable should be of type integer, because this is a pointer to an integer. So we cannot make this variable short int and write this statement. This will be wrong. This will be not allowed by compiler, because this particular pointer is a pointer to an integer. However, here we are making it a pointer to a short integer. So this will result in wrong answer. And there is a reason for that. So and that reason is explained now. So we assume that we have a variable int var1, so its value is basically 5. We have another variable int var2, its value is say 9, and we have a pointer int var1 underscore pointer, and it is a pointer variable, so we need to put an asterisk after that, and var1, and we have another int star var2 underscore pointer equals and var2. So basically we have two variables in the memory. var1, we assume that var1 is stored here with the value 5. So and immediately after that will be stored a variable of 4 bytes, because it is also of type integer named var2, and it will be holding the value 9. Now what happens when we write cout var plus 1? What is written on the screen now? We know that when we write var plus 1, it is the thing that is written on the screen is basically 6. And if we, however, here the difference comes in the simple variable and the pointer variable. If we write var1 underscore pointer plus 1, ideally var1 was basically pointing to this address 0000 So when we do plus 1, if our concept is not clear and we think both things are same, what we would do here is that we would basically add 1 in that particular address. However, that is where the pointer variables are different from the from the simple variables. When we are writing var1 underscore pointer plus 1, it technically means that 1 multiplied with the size of this variable to which it is a pointer. Size, it was a pointer to an integer variable var1, so integers have a size of 4 bytes. So this basically means var1 underscore pointer, that was an address, plus 4. So it technically will print on the screen 00000008 and not 00000005. Just like in case of a simple variable var1 plus 1, it would have printed 5 plus 1 6. Here it does not add 1 in the address. It technically multiplies it with the data type. Similarly, if it was a short int, and this also needs to be short int, then it would have occupied 2 bytes in the memory, these 2 bytes, if it was short int. So if then we would have done var1 underscore pointer plus 1, it would have written 0006 here, because here it would have been multiplying 1 with the size of the variable to which it is pointing, and this time it is pointing to a short int, and short int has the size of 2 bytes. So it will be printed 6 on the screen here, because it will be multiplying it with 2. Similarly here, if it is var1 plus 3, here it becomes 8. However, here it becomes, if it is plus 3 in the pointer variable, it does not add 3 in the address. It basically multiplies it with the type of the pointer. This was a pointer to a short int, and short int is of 2 bytes. 2 multiplied by 3 is 6. basically it will add 6 in A, 1, 2, 3, 4, 5, 6. So it will print on the screen A now because 3 gets multiplied with 2 here. So that is the difference between a simple variable and a pointer variable, and that is exactly why we cannot assign a short int pointer to a integer variable or an integer pointer to a short int. Because it is not compatible and it is not allowed by the compiler. And the next thing, and that is associated with it, is the reference operator. This basically is a reference operator that helps us reference this variable. This variable had a certain address in the memory, and by using the reference operator, I ampersand sign or and, by using and, we can reference this variable. We can access its address. So we had accessed its address here, and now the address, it contains the address when we have written this line. So this operator is known as a reference operator. It should not be confused with the reference variable that we had studied a bit earlier. Here, in the reference variable, the ampersand sign was on the left side of the equation, like int var1 equals to variable 1. Here it means a totally different thing. It means defining a reference variable when it is on the left side of equation. Here it is basically on the right side of equation. So here it is basically used to access the addresses. So here you have to be careful with this operator. You can call it reference operator here, and you can call it ampersand or and here for reference variable. Or it is also a reference operator, but to make a certain difference. So that is the reference operator. Now we have seen the reference operator. Now let us look at the dereference operator. We know that we can define and initialize pointers just like this. In definition, we have to put an asterisk with the name of the pointer variable, and then just like simple variables are filled with the value, pointer variables are filled with an address of another variable. So what happens is that, for example, here it was our RAM, and the variable VR was stored here at the address 00000004, assuming it is a 4 GB RAM. So pointer variable, when we write this line of code, pointer variable holds the address of this variable. It means that this pointer points to this variable. So when we write the cout ptr underscore var under a pointer variable, it displays this particular address. However, just like we had a reference operator here, we have a dereference operator. Reference operator used to access the address of this particular variable. It was used to reference this variable. Similarly, dereference operator, that is also a steric, that is used for dereferencing dereferencing this address that is being pointed to by the pointer variable. And dereferencing is basically kind of meaning here, if we are not referencing the address, however we are receiving the value from that particular address that is being pointed to by the pointer variable. So whenever we are writing a star with the name of the pointer variable elsewhere from the definition, it is basically called the dereference operator. It should not be confused with this here. When we are defining, we write an asterisk in order to tell the compiler that it is a pointer variable. However, when we are putting the star along with the variable name elsewhere apart from definition, it means that we are dereferencing that particular address. We are not referencing the address. We are not referencing the variable, we are dereferencing that variable. We are not accessing its address, we are accessing its value. So when we write cout star ptrvr, so ptrvr was pointing to this particular address, and we have a dereference operator along with that. It means that whatever will be written, whatever value will be written on that address will be picked from here, and what will be displayed on the screen will basically be the 10. We have not referenced this address, however we have dereferenced its value. So similarly, we can of course manipulate this value. Here we access that particular value by a dereference operator. We can manipulate it as well. Just like if I write star ptr underscore var, what will happen equals 9. What will happen is that it will basically go at the address pointed to by this pointer variable, and we have a dereference operator along with that, and it will dereference that value to 9. So we have changed the value with the help of a pointer variable. Now that pointer variable was basically pointing to the another integer variable. So dereference operator can be used to access as well as to manipulate the value at the address that is being pointed to by a pointer variable. Pointer variable was basically holding a certain address, and when we are using dereference operator with that pointer variable, it can basically access as well as manipulate the value that is being pointed that is being stored at that particular address. So that is the dereference operator. We started with the understanding of RAM, then we saw how pointers are defined, how they are different from simple variables. Then we saw about the reference operator, and after that we saw about the dereference operator. Dereference operator should not be confused with this asterisk that is used during the definition of the pointer. Similarly, this reference operator on the right side equation should not be confused with the reference variable definition ampersand sign that is basically used while defining reference variables. And then at the end we saw how the dereference operator can be used to access as well as manipulate the data that is being pointed to by a pointer variable. So we can go to that address and access this value as well as manipulate that value by the dereference operator. So that's pretty much it from the introduction to pointer session. So that's it.